Right, so today we're talking about CLICKdesign. So we are about performance specification of wood in construction. And this is a very, very deep topic, of course, that many have researched. So we drew together a team to look at this challenge once more. You can see the pan-European nature of the partnership on screen, and also some quite happy, smiley team members at the end of our final meeting at the end of May in Isla in Slovenia. And really today is a celebration really of that hard work, that effort, that coming together, the development of new knowledge, but critically as well, when we think about specification of wood and tools and presentation, it's about how we can enable an understanding of wood to ensure appropriate specification and fitness for purpose. Oh, it's not moving. God. Oh, okay. Thank you, thank you. So again, I'm sure many of you were in Helsinki almost 3 years ago. Sort of cast your minds back then when nobody had heard of coronavirus, or very few people anyway. It just seems like a lifetime ago, really. But at that time, I remember presenting this slide and talking about the confusion that exists within a design office, an architectural practice, around the performance of materials. And it occurs in lots of different areas within the sector. About, well, how long are these wood products going to last in particular environments and particular end uses? And you'll get a number of different answers depending on our national sources, our inventory of European or ISO standards, for example, or indeed, in some cases, people talk about the rather arbitrary, reasonable working life for products. Now, that's a bit of a challenge. So clearly, it's a struggle. It doesn't enable or access the appropriate specification of wood based on a performance characteristic, which is really critical, we think. Its information around service life obviously is critical in underpinning applications in building information modeling, in life cycle analysis, and improving that presentation of wood as a construction product and a construction material. So we were concerned then, and to a certain extent less so now, about wrong product being used in the wrong application, and of course that impacting on people's perceptions around reliability and performance of wood in a lot of different end uses. So our role was to develop a protocol to enable a more informed decision-making process towards the specification of wood in construction, and moving from this rather sort of fragmented approach to a much more consistent, knowledge-based decision-making process. And again, I would have presented 3 years ago, this was our original schematic around the project, which obviously fundamentally had to look quite closely at all the work that had gone before and extracting the best elements from it, and about how those would link together. And then particularly for this, we had focus on pan-European application, so it had to critically understand, develop, and deploy information around decay and integrity, but it also had to do it for aesthetics, which is a very critical performance factor for exterior wood uses, and it also had to do it for termite and insect performance, so that relationship around some of the other critical biological hazards that the material faces. And then really it was about that coming together and presenting it as part of an integrated process to support knowledge deployment and appropriate specification. And that challenge is not to be underestimated. It's a challenge that the European standards community has been wrestling with for the best part of 15 years. But I can say very happily, actually, that has progressed significantly as a result of this project and program. So I think I am stopping there, and what I would like to do now could we do the transition to the video? Just to sort of take a slightly different perspective on this. This is not a European issue. So we're now going to just flick to Jieying Wang from FP Innovations in Canada, just to talk a little bit about the work they do. So we're in this challenging situation of understanding a material that becomes a component, that becomes a building, and the performance wrapped around that. So
if production, can you get this? Yeah, perfect.
Can you play? Do we have sound?
I think we have, but a very low volume.
I think we shouldn't touch anything. It's better if production can.
Yeah, they. Do we have a solution for that, production team?
In recent years, we have focused on energy-efficient buildings to support the regulation to reduce energy consumption and GHG emissions from...
Can we restart?
Hello, my name is Jieying Wang. I am a senior scientist with AP Innovations based in Vancouver, Canada. I do research in the durability and energy efficiency area. Just a quick overview about our work on durability by design. We have focused a lot on performance monitoring of wood-based buildings to support developing best practice guidelines for design and construction. The work includes both light wood frame and mass timber, new buildings, and retrofits. In recent years, we have focused on energy-efficient buildings to support the regulation to reduce energy consumption and GHG emissions from the built environment. We have also focused on mid-rise and taller buildings, mass timber in particular. Ensuring long-term durability is critically important to maintain and expand the market of wood in those building sectors. For field monitoring, we measure parameters such as the basic moisture content of wood and its service conditions. The moisture-related problems are most often caused by rain during construction or in building service, especially in the coastal climates. They are also caused by other moisture sources such as high humidity. The field monitoring directly provides performance data for innovative solutions. We also use data to validate design expectations, assumptions used in engineering, and modeling tools such as WUFI. We do the research in close collaboration with architects, engineers, contractors, academia, and government. I want to thank you for giving me the opportunity to talk about our research in wood durability. Best wishes to you all.
That's great. There's a couple of words that really jump out for me there. One was around greenhouse gas emissions, which of course is a big part of our motivation around deploying wood in construction. The other one was the reference Jay made several times around moisture. And it's not just timber, of course, it's any construction format. Moisture, water ingress is a real serious challenge, and you will see as part of our work when we get to that point today. So I think we're going to move now, yes, into Menti. So just gaining a few sort of early views and opinions from our audience here in the room and online. So first of all, if we could ask you to just drop a pin on your home location on the map that should be on screen. Oh, very good. They are starting to appear.
How do you drop it? You just click on it. Or click on it.
The accuracy of the map might be slightly off, but we'll gain a good impression. Maybe you can see where your pin is dropped. Clearly, somebody lives in the Orkney Islands, which I'm very surprised about in the United Kingdom. So interested to meet that person soon. But here we are, and it's a bit of fun, but actually this is a really important part of our conversation today, is around location. And location tells us lots of things. But I think from a wood perspective, it also tells us a lot about traditions and practice and forest culture within particular regions, which varies enormously across Europe. So our next port of call, so thinking about that location, your home location, I want you to estimate or decide what you consider to be an expected service life for 3 different products. We've got a fence post, so that's the element that's going down into the ground on that left-hand picture. Exterior wood cladding, and we have a timber, well, it's a footbridge actually, a pedestrian bridge there. So you have a slider, 0 to 10. 0 might represent less than 10 years. 10 is 100 years, and then increments along that scale. So 5 on that scale would be 50 years. So here we are. This is quite interesting as the live data comes in. So this obviously reflects on our own personal experiences. We might have had a fence in our garden, or we might have wood cladding on our building, or we may even have a wooden footbridge, who knows. But this is quite interesting. So at the moment, perhaps the order is not terribly surprising, and we might want to think about, well, why that is. Some of these products we might be a bit more accustomed to replacing on a more frequent interval than others. So our timber post in the ground is coming out at 1.7, which, well, let's, for the sake of argument, say that's 17 years. Our cladding is 4.1, so 41 years. So that's a pretty decent expected service life for exterior wood cladding, perhaps. Although we all, I'm sure, might be able to cite examples where it is much, much older. And therein comes part of our culture around maintenance and looking after buildings, and our heritage as well. And then our timber bridge, we've pushed into the 50-year service life bracket. So that's really interesting. And I'm sure if you spoke to colleagues in different regions that we saw on that map earlier, you may see some subtle differences around expectations, around the challenge that that particular environment is located in, that product is located in. So already we've started to think a little bit about performance, what that means, what we expect as owners or individuals or people interfacing with wood products. But I want now to sort of hand over to the real heart of CLICKdesign project, which is the essence of what we've been developing and building. So I want to hand over to Jonas Nikluski from Lund University to take us through the various components of our output. So,
okay.
Thank you.
Many thanks, Ed. So the heart of the expectations are increasing. Can I get the presentation here? Perfect. So thank you, Ed. I'm Jonas Nikluski from Lund University, and you're stuck with me for the next 20 to 30 minutes, where I will talk about the science and implementation of the tool, with S in brackets. And I would say that the heart of CLICKdesign is, and the core idea is to, bring together researchers with different perspective of durability, and then further our work on durability and research. But also a very important part of CLICKdesign has been to kind of synthesize our knowledge and make it available. So not just available in the sense of publishing open access, but make it actually available for the public, so for anyone to use. So this is what we have. Our attempt has resulted in the CLICKdesign tool, which is actually a set of 4 different tools or single-page applications. So I would say the core of CLICKdesign is the science, of course, because we are researchers, but the kind of bridging the gap between science and the public is the tool. So I'm going to talk about that. And this session is structured so that we have asked 4 different researchers in CLICKdesign with 4 different backgrounds and 4 different perspectives, what durability means to them. So we're going to have 4 different people speak here. And first up is Philip.
Does the mic work? Okay, there we go. Good day, everyone. So I'm Philip Bester van Niekerk. I study at Göttingen University in Germany, but originally I'm from South Africa. So, do I just click?
Yeah.
Okay, let's see, presentation. It's moving. Okay, perfect. So, if you would ask me what durability means for me, then specifically, it's my job to tell you that it has something to do with fungal decay. So, what is fungal decay? And if you refer to this picture on the screen, you can see that decay is a very important process in natural ecosystems, and it is fundamental to the carbon cycle. However, sometimes this process goes into like our everyday lives, and if you have specific building materials, then this actually causes our material, which is wood, to be outcompeted by its competitors, as you can see in this castle in Lithuania. So we know, and most of you in the crowd are familiar with structural engineering design guides. However, there's not so many in terms of durability design. So we obviously have this ISO standard 15686, which is a general one for all sorts of materials. And then there's a few scattered guides on timber exclusively, and this is an example of one of them, the Australian Timber Service Life Guide. So in Europe, we then try to create our own approach. And this was our predecessors as well as what we were working on. And pretty much the design principle that we are following is this simple one that is actually informed by ISO. So you can see that it says that the exposure that our material would be subject to during its design life should never be more than what it can sustain or handle. And if you consider fungal decay specifically, then exposure for us means moisture and temperature, and that can create something which we refer to as a dose. And dose, if you have enough periods of dose or accumulation of dose, you can expect a response in the form of fungal decay. And so if you then have a material that has a specific durability characteristics, that will influence the threshold of how much of this dose exposure it can handle. Okay, so just to quickly run through the process, the modeling process that we have. So the first thing is we have an exposure model. Jonas will quickly show you a little illustration of that. But it's pretty much we have to take climate variables and we have to somehow get from the climate to the material climate, which is the moisture content and temperature of the material. And so once we have this, we can then inform ourselves of a sort of a risk ranking on a daily basis. So if you consider this graph here, your x-axis is either temperature or moisture content. And the first one is actually the temperature curve. So on a daily basis, you would get a ranking from 0 to 1. And you can see how the curve, what value, dosage value the curve would give to a particular risk ranking on that day. So if we then consider a particular time series, you can accumulate this amount of dose on a daily basis over a certain period of time. And we know that sometime this summation would lead to what we call a limit state, and there's various limit states that you can choose. But we decided specifically on the onset of decay as our limit state, because we know that once it passes this point, it's extremely chaotic and very difficult to predict what happens with the material properties after this. So we say that we'll terminate service life in this context that you will see for fungal decay specifically at this onset of decay. But we've got a other researcher that will briefly introduce maybe the possibility of if we extend this limit state. Right, so you might be asking at this point, so how is all of this sort of procedural, this mathematical process important for you, and how can you use it as a designer or architect or engineer? So I just have a quick case study. So for instance, if you have this horizontal reference board, so it's made of Norway spruce, it's 1 meter above the ground, and we placed it in 500 different locations over Europe. And so if you would then model the amount of dose that it experiences during an average year, so that is in a typical year of the last 20 years of climate data, you would see that you get these bands of dose that's being produced over Europe. And so if you fall in a dose of 10, you can expect that reference material, that board, in a horizontal orientation to last 23 years approximately. And when you have a very high risk region, in a 70, you can expect something like 3. And so if you want to then change your design so that you can have a service life of what the building standards dictate, then you would have to change the durability rating of the material. So you can use either a treatment or modification or just a naturally more durable timber species. And Jonas will also show you some things of the influence of joints, etc. So that's all from me. I went a little bit over, but I think that's fine. Thanks, Jonas.
Thank you, Philip. So now that Philip has provided us with some background, I'm just going to tell you very briefly, before I show you the actual application, how this was implemented. So how this was kind of structured, how the science was structured to make it more available for public use. So this is all very complicated, but I'm not going to go into the details at all here. I'm just going to say that, as Philip said, we have 2 different sides of the equation here. One is exposure, which is really all about modeling moisture content due to different climate effects, but also different detailing and different sheltering effects and so on. And then translating this to a decay progression through a dose model. So we have exposure on one side, which is all about modeling moisture, and then we have, so this is, here we're using a lot of finite element simulations, but in the application everything is pre-calculated because it's quite time consuming. But on the other side of the equation we have the resistance, which is all about the material, so how many doses or how much exposure the specific material, like a species or a treatment, can take before it progresses into severe decay. And here we have a lot of measurements, but also a model to translate those measurements. There are some standardized measurements that can be translated to a characterization of material resistance. That is in terms of doses as well. So when you reach a specific amount of doses, you have decay. And to make this all available, we have done a lot of pre-calculations of different exposures. So we have looked at different climates, different detailing, and different sheltering effects. Everything is pre-calculated. And then we have a material database which describes different materials and how well they behave under specific circumstances. So with this, I want to show you the very basic interface of the decay module of the tool. Let's hope the video plays. Yep. So this is a single-page application which is available in the browser, which basically guides you through a number of design choices. So you have, for example, first of all, you have to decide if you are in ground or above ground, because the conditions are extremely different. And as an example, I'm going to use my own timber deck at my the house, and this is something I built last summer. Unfortunately, when the price of timber increased by a lot. But yeah, so obviously this is above ground, so I'm going to select above ground here as the model type. And then I live in Skåne, southern Sweden, close to Lund. So here you can see a small dot that a marker clipped to, and this is one of the locations we have chosen for pre-calculation of different effects. So climate is obviously very important, as Ed also mentioned. Another important factor is the detailing. If you have exposed end grain, then the wood will absorb a lot more moisture, and that is of course favorable for decay, so that is something we want to avoid. You might also have contact faces between different members, and that is also bad, because once the contact interface becomes wet, then the moisture will not be able to dry out. So here I'm just going to model a horizontal face of one of my decking boards. So I did not select any type of detailing at all. And then we can have sheltering effects. Obviously here I don't have any sheltering effects, but you could have like roof eaves or other effects protecting from rain. And then most importantly, it's the choice of material, perhaps. That's where we are struggling the most when we are selecting the material among a huge number of different products. So here I just selected Norway spruce, because that's something we're all familiar with. And if I do that, I end up with a number of about 7 years, which is when I could expect the first signs of decay on my spruce decking boards. That is quite an optimistic view, because I also have some end grain faces here, also with some contact to other members. So already after 3 years, I might expect to have some kind of signs of decay close to the end grain, according to this model. And that is not something I want to deal with in 2 years from now. So probably I should select a different material. Spruce, untreated spruce is not really so common for decking. That's for a reason. So I might choose larch instead, which is quite common in Sweden for decking. And then I can see that just changing the material, the service life increased by quite a lot. Now I'm too quick, but it was around 15 years, I think, for this detailing. And then that might not be enough, so I might go for a treated material instead, which is ultimately what I decided to go for. So hoping it's maintenance-free for a few years. So that is very, very briefly our basic single-page application for estimating the service life of wood. That was the first perspective, and now we kind of put that into the context of a tool. Next, we will hear from Peter Radil from VTT, who is a structural engineer, so he's perhaps more concerned with the structural aspects, like the loss of load-bearing capacity if a beam or a column is subject to decay. And unfortunately, he could not be here today, so I have received a video which should play now, hopefully with sound and also some nice music.
Good morning, my name is Peter Radil and I'm Senior Scientist at VTT Technical Research Center of Finland. Today I will be talking about the durability of wood construction. For me, durability is a very important concept. It means the ability to withstand the harsh external conditions, rain, snow, solar radiation, and also biotic damage during the whole life of the building. One may think the durability of wood is just a property of the material, but this is only part of the story. Durability of wood construction is a combination of material, its protection, let's say coating or impregnation, and detailing and overall design of the construction. Combination of all these factors can contribute to the overall durability of wood construction, and indeed we have many buildings which are performing very well for many decades or centuries. At the same time, we have buildings that are failing after a couple of years. Certainly we would like to design buildings lasting for centuries, but it can be challenging even to reach the requirements of the design codes, which are 50 years for residential buildings and 100 years for bridges. That's why the research of durability of wood construction is very important, because it can provide a deep insight into the processes that are happening before the degradation of the material starts and during the process of the degradation. For me, as a structural engineer, the limiting factor would be the onset of decay. Basically, no structural degradation would be allowed. But for me, as a scientist, the situation is different. I am always curious what is happening beyond this point. And thanks to our great partners from CLICKdesign project, we were able to make a model of the structural integrity during the decay of wood. Structural integrity is a concept based on the knowledge of structure, detailing, connections, and the mechanical properties of the material. The loss of structural integrity means that the durability is also over, but the onset of decay doesn't mean that the structure is automatically collapsing. So even if this is not acceptable from the point of view of the designer, this information of the structural integrity beyond the point of decay could be very important or useful to people who are dealing with the maintenance of existing structures or with the critical infrastructure. In the next presentation, you will see the demonstration of an online tool that we developed in the CLICKdesign project. This tool predicts the development of the most important values for the assessment of structural integrity over time, which are the material mechanical properties like compressive strength or bending strength of the material, or the reduction of the cross-section in time due to decay. I would like to say that with a better knowledge of durability of wood construction, we will be more confident to design wooden buildings for a certain lifespan. We will be able to plan better the maintenance of such buildings, and definitely at the end of life of the building we will know the value of the components integrated in that building. And maybe the end of life of the building doesn't mean the end of life of the component itself, and it can be reused, saving a lot of CO2 emissions in the process. That's basically the end of my message. Thank you very much for your attention, and I wish you a very nice day.
Okay, thank you, Peter. So, as I myself also have a background in structural engineering, so for me, it makes sense to define, service life as when decay begins to set in, so the onset of decay. But as Peter said, this doesn't necessarily mean that the building will collapse at that point. So it might be interesting to see what happens beyond that point as well. So that is what we have tried to do here. Oops. Let's see. Okay, so our objective here was to go beyond what we have worked with previously, which is the onset of decay, and see how we can connect this to the residual structural capacity of a structural component. So what we need here is, again, the exposure, because the exposure, it determines how fast the deterioration rate in terms of fungal decay. What we also need, what we really need is perhaps the mass loss, because we cannot, as Philip said, the dose is kind of related to the decay rating, and the decay rating doesn't relate to, doesn't transfer easily to structural integrity or strength. So what we are maybe more interested in mass loss. So here we have one model which translates the dose to equivalent mass loss. And then we have in CLICKdesign developed a model based on a lot of measurements done in part by Philip, or entirely by Philip, where the mass loss is connected to the residual strength. So based on mass loss, we can kind of correlate or calculate the residual strength of a component. And then you will see that we have two different ways to present this, either as residual strength for a given mass loss or a reduced cross-section, similar to how you would deal with a damage caused by fire, as we learned yesterday. So this is the mechanical module of the tool, which was developed at VTT. So I'm not going to be able to explain all the details, but the principle is quite simple. So essentially you have a few design parameters, which is basically your cross-section and the timber quality. The length is not important here, because this is just a residual capacity of a cross-section. So here I'm just going to select an 80 by 80 cross-section with a quality of C20. And then the exposure is important. You can get that from the previous, so based on climate, detailing and so on, you can get that from the previous module. And then you have a few selections here. For example, the mode of decay. Brown rot would be the most aggressive and the most common as well, at least in above ground applications. And then based on this, you can see how the strength decreases over time for the specific exposure conditions. And in this case, you have the reduced, the residual strength in compression and tension and bending. But as I mentioned, you can also calculate the equivalent residual cross-section, assuming that you have a layer of deteriorated wood and a core of sound wood, which is unaffected by decay. So these are just two different ways. I would say that the framework as such is quite experimental. There are a lot of uncertainties involved, but it's a proof of concept that is based on a lot of modeling and experiments. So that is basically it for the mechanics, and we will jump straight to Jakob Sandak from Inner Renew, who has a different perspective on durability. And he unfortunately could not be here today, so he has also recorded a video. Oh, the sound is probably...
What is a durability for me? To be honest, it is a very tricky question. In the context of building, the durability can be defined as a material property linked to the intrinsic resistance against deterioration. But the deterioration can be of very different nature. It is relatively intuitive to imagine durability of wood as regarding fungi or insects. In this case, we know quite a lot about mechanisms, kinetics, biology of microorganisms, as well as protective technologies. It is a bit more complicated to define the meaning of durability in the context of aesthetics. Within the CLICKdesign project, we identify this as an extremely relevant factor, in several cases determining the effective service life duration of the structure. In fact, the decision to replace or renovate the building is in majority of cases triggered not by the functional or safety failure, but due to the aesthetical reasons. However, when thinking of aesthetics, sooner or later we face a challenge of understanding people, or better to say, reading our minds. What is a beautiful facade? What is acceptable discoloration? At what stage we will not tolerate anymore the deterioration of our building's appearance? These are very complex questions that must be addressed at some point, usually by the architect. Of course, each answer may be very different for every person, depending on our culture, local tradition, life experiences, etc. The perception of beauty may also evolve during our lifetime due to the changes in trends, availability of new technological solutions, or gaining new experiences. Nevertheless, the worst what can happen is to disappoint building users who complain that they did not expect any aesthetical changes. But every material changes in time, not only wood. The extent and kinetics may vary, of course, depending on the material choices, architectural detailing, or local climate. But there is not any black magic in aesthetical deterioration of buildings. It is rather a response of the material to the complex mixture of factors that can be expressed as cumulative weathering dose. And this was exactly our approach developed during CLICKdesign project. Our dream was to integrate the knowledge and experience of the project partners that we had and to provide a visualization software capable of simulating changes to the building facade appearance. The algorithm evolved from modeling of simple walls uniformly exposed to natural weathering toward the demonstration of simulation possibility for very complex buildings designed in BIM. Of course, the varying locations, climate zones, and construction details were carefully included as important simulation variables. Fortunately, building physics is very well established nowadays, and various engineering tools help us a lot to map material climate at each position over the facade surface. Finite element methods are perfect for simulation of temperature, solar radiation, as well as wind-driven rain. Therefore, we managed to properly identify dose distribution over the entire building scheme. Another challenge was to understand how different biomaterials change color when exposed to weathering. For that, we used results from the proceedings experiment, where we tested 120 different biomaterials that were exposed to natural weathering conditions for a period of 2 years. Having established scientific basis for the simulation and visualization, it became possible to build a prototype software that you will experience in a few minutes. As you can imagine, we finally have a unique tool that can help to make a proper decision regarding material selection, architectural detailing, and the most important, assuring customer satisfaction. Thanks to that, we can also estimate the expected service life, maintenance plan, as well as environmental impact and lifestyle costing. Going back to the question, what is durability for me? I can only say that it is a fascinating scientific challenge to make buildings that last long, being continuously beautiful, environmentally friendly, and cost not much.
Jakob Sandak's view on durability, aesthetics is where he comes from. So what we try to do here is that, as Jakob mentioned, aesthetics is all about, for at least one, it's not all about it. One aspect is the color change. That is one big factor. But the other factor is that this color change will depend on, the exposure conditions, mainly on solar radiation and exposure to precipitation. So basically, what we have here is a framework where we have exposure, and that is, as I said, radiation and rain. And to analyze a building, it can quickly become quite complicated because you need to know the exposure in all of the different points on a facade, for example, to be able to translate that into a dose and ultimately a color change. But there are tools available. For example, Jakob talked about CFD analysis. We've also worked with some more simplified methods in CLICKdesign. But this is not something that is easily available for the public. So again, what we have done here for our public-facing tool is to make a lot of pre-calculations. So basically, we do CFD or similar environmental analysis of an example building. We obtain a dose map which shows the exposure at different points in the building. And then we have the material database where you can choose a material and see how the color of this specific material changes over time. And this is obtained from measurements. And then we have from digital images over time at different exposures. You have these RGB curves. So you can see how the color of late wood and early wood changes with time and with exposure. And ultimately, what you can then do is that you can model the long-term aesthetical change, or at least the color change of the facade to some extent. So now I'm going to show you the prototype of our tool, which is, again, everything is pre-calculated, and we provide a few examples. So this is a very simple floating cladding, as you can see here, with some generic wood texture and in a very basic environment. And then as a user here, you can choose different materials, and this will, of course, what happens is that you toggle between different color curves. So the color change is connected to the material. And then you can change the exposure, or in this case, time. So as Jakob mentioned, the measurements were done in a period of 2 years, but after 2 years, the material is more or less fully weathered. So and then you can change between different materials to see how the color of this specific material changes over time. This is some thermally treated spruce, if I read correctly, and most materials tend to turn gray after some time. So this is just a cladding. We might have a more complicated building. This is a playhouse I got from Swedish wood, just to test the concept on. So here you have some very deep eaves and some overhang protecting the decking. And if you do a CFD or environmental analysis here, you can see that the eaves will protect the part of the cladding against driving rain. So these regions will not become weathered at all. And I'm sure you've seen this in some buildings with unpainted cladding and deep eaves. Again, for different materials, you can see this is not yet photorealistic, I would say, but you can see the concept, and you can prepare the consumer that they should expect some effect like this, and if they don't, some think it's very beautiful, some see it as some kind of deterioration and damage, and then if that's how you see it, then you might want to paint or use a different wood product. Okay, and now we're going to jump to our fourth and final perspective on durability, which is from Magdalena Kutnik from FCBA in France, and she works with, well, I shouldn't spoil what she works with. She will give her perspective on durability. Which is termites.
Work package 5 of the project focused on termites and other wood-boring insects performance. We had 4 main objectives. Our first task was to make an inventory of wood-boring insects. Indeed, the identification of insect species harmful to wood and derived materials is essential in order to efficiently monitor the movement of insect populations over long periods of time and to anticipate the risks of invasions from new territories. The risk for a material of being degraded by insects relies on multiple parameters. Our next task was to identify and categorize these parameters. Because termites are able to degrade various construction materials, it was essential to measure the durability of relevant construction materials and to attempt predicting their performance in different situations of use. Finally, we translated the knowledge gained into a predictive tool which takes into account the insect risk and explains how to handle it in infested areas. Based on reference publications and questionnaires sent to European experts, we identified 83 insect species causing damage to wood, which evidence of attack can be found in buildings. Global warming affects the distribution of insect species, especially of termites, which are more abundant in warm areas. It also increases the risk of introduction of invasive species, which may show different feeding and nesting preferences. We updated the distribution map both for subterranean and drywood termites, including new data we gathered on invasive termite species. The parameters influencing the insect risk have to be split into 4 groups. The first one is related to climatic conditions, the temperature playing a major role, and environmental parameters, such as, for example, the nature and moisture loading of the soil in the case of subterranean termites. The insect occurrence depends on the geographical region considered. Then, the durability of construction materials and the construction rules that are defined to ensure their proper use are of paramount importance. Insects exhibit difference in their behavior, life cycle, and feeding preferences, which has to be taken into account for estimation of the threat they represent for wood-based construction elements. Finally, human behavior is also part of the story. In particular, the strategies we adopt to prevent and manage insect risk in our living environment. Different experimental approaches, standardized or not, can be used to assess the inherent durability of wood and wood-based products against subterranean termites, including engineered products and modified wood, and also the efficacy of preservative products. In the case of performance, which can be defined as the ability to withstand degradation over time, we currently don't truly have one single recognized or standardized method, which means that our estimation of performance is mainly based on long-time experience and on the issues of field tests. We also lack performance criteria and predictive tools for service life of wooden elements when it comes to insect risk. Within the project, we decided to carry out durability tests on a set of 19 materials provided by the project partners, which are natural woods, modified or engineered wood materials, bio-based materials. We tested their resistance against 1 to 3 species of European termites, differing in their biology and thus possibly in their aggressivity towards the test materials. Then we explored the possibility of developing performance tests through an innovative experimental approach. Our conclusions are that durability and performance are distinct properties which should be evaluated alongside. The recommendations for end-use applications of wood-based materials, such as indoor or outdoor use, should take into account both their class of durability and their expected performance in real-life situations. Setting up predictive tools for performance requires multidisciplinary approaches. A new distribution map has been proposed for the 2 main beetle species known to cause significant damage to wood used for building purpose in Europe, the furniture beetle and the house longhorn beetle. Furthermore, these 2 species are the models used to evaluate the efficacy of wood preservatives according to European standards and biocidal product regulations. The key question is how far from the current distribution range these species could spread in 20-50 years. In order to strengthen the available monitoring tools, we attempted to build up for the first time a European termite hazard map inspired by those made in the US and in Australia. Prevention of insect attack is always preferable to remedial control. This can be proper architectural design, avoidance of construction details that may trap water, efforts made to ensure that structures prone to termite infestation can be easily inspected. In order to help architects, designers, builders to anticipate and manage the insect risk, a guidance tool to handle the parameters influencing the insect risk has been prepared within the project.
It's bringing us the perspective and aspect of termite risk. So basically, termite risk for us was less about modeling and more about mapping. Well, perhaps the most important question you have to ask yourself if you're building something is if there is a risk or might be a future risk of termites. And if there isn't, then you don't have to care about termites. As, for example, in the Nordic countries, we don't really think about preventive measures against termites. But termites, they like specific climates, and due to climate change, we can expect to see some kind of expansion of the termite-infested regions of Europe. So one part where modeling came in is modeling the future risk of termites. So basically we have, what we have done here is that we have mapped out the present risk of termites from experts and just from the knowledge in Europe. And then we also try to model the risk of termites, and then using this model we can also predict the future expansion of the termite region. So I'm going to show you the tool we have here, which is all about mapping. So here you have an interactive map, basically, where you can look at the distribution of different types of insects, for example, termites or beetles. You can also look, if you're interested, in a specific species of termites, for example. This is a quite coarse data set, I would say. For example, you can see that entire Germany and UK is they are infested by termites, but really it's just isolated cases. I think Germany had like one case, and you don't have to worry too much. But the idea is to inform the public if there is a risk of termites and other insects, and if you have to take any measures, preventive measures to protect your building. And then you can also see the modeled, here you have the modeled contemporary or present risk of distribution of termites. And you can compare against different climate change scenarios and see if there might be a future risk in 50 years or so. And then if you are at risk, you might be interested in the natural rules that apply, and then you can click a country and you will have a lot of natural information about how you can deal with termites. And then we also have a database of durability classes for different materials. Okay, so that was 4 different perspectives and 4 different interpretations to my question, what is durability for you? You have 5 minutes. That's basically what they got. And all of this is open source and available and can easily be found. We are working on a better domain. This is my personal GitHub. And can also be, everything I showed you now can be reached through a single, from a single link here. And especially note the big disclaimer at the bottom. Okay, I think I jumped the gun there.
Okay.
Yeah.
Great, thank you very much, Jonas. And as you can see, what might seem quite a simple question interpreted in 4 very different ways, and the complexity of the work that has come together within CLICKdesign. I also now just wanted to make an acknowledgement of a bit of a bonus, really, associated with the project, something, again, like coronavirus, we never anticipated 3 years ago. And we've heard mention a couple of times this importance of transferring knowledge. Publication is one thing, but it's how we enter all that information that we've been generating at the right level to improve understanding of performance of wood products. So I just want to acknowledge Nežka Šetincic in a Renew Centre. So we worked with Nežka completely unexpectedly as a PhD candidate in education and psychology on looking at educational video content to support the the sorts of areas you've been hearing from the team today. And we have a bonus collection of YouTube content on Nežka's site about why wood and service life, about degradation processes, material specification, that critical element about protection of design, that first principles of when new things are being built or renovations are being proposed, and also about maintenance. And I think if I click there, is that going to run automatically? Do I need to do anything further? There was a video.
Maintenance.
Yep.
Proper design can greatly reduce the rate of deterioration, but all materials need some kind of ongoing care. Maintenance is vital in preventing many issues and prolonging wood's service life. This is usually accomplished by applying surface finishes that can function as a protective measure, aesthetical measure, or both. There is also the option of leaving the wood untreated to achieve a gray or silver effect. But in this case, the user should be aware that not only will the wood weather and dry faster, but it will do so more unevenly. Broadly speaking, there are two types of coatings: film-forming coatings and paints, and penetrating oils and stains. As the name suggests, film-forming coatings create a durable film on the wood surface that acts as a physical barrier to the elements and insects. These include clear and semi-transparent coatings like varnishes, and opaque coatings like paint. Pigmented products offer better protection from ultraviolet radiation since they block sun rays before they reach the wood, making them more resistant to weathering. However, these products cover the wood's desirable aesthetic properties, such as grain and texture. In contrast, clear coatings bring the authentic wooden surface to life, but allow UV rays to penetrate and absorb into the wood. While film-forming coatings are marketed as long-lasting, they do tend to crack and flake if not maintained regularly. Cracks and flakes in the coating or paint allow water to enter and become trapped between the wood and coating, creating a perfect environment for decay. Once cracks, peeling, and blisters start to appear, the coating needs to be removed completely from the wood before recoating, creating a lot of work for the owner. For this reason, film-forming coatings are not recommended for highly exposed areas. Oils and stains, on the other hand, work differently than other coatings. They penetrate the wood and preserve it by soaking into its fibers. Since these allow the wood to move, there are no cracks, peels, or flakes, but oils and stains will wear away through time and become patchy. These types of treated surfaces can be recoated directly without scraping or sanding, typically every 2 to 4 years. So how frequently should exterior wood be maintained? A coating's efficacy strongly depends on type and climate, and different parts of the same building may experience varying amounts of sun, wind, and rain, so there is no one-size-fits-all time frame. In general, recoating should be done when the treatment is beginning to show signs of failure. Every year, owners should inspect for cracks, flakes, and blisters in the coating, faded colors, the condition of connectors, and possible signs of water, such as moss or algae. Even though mildew is not harmful, it indicates conditions that are favorable for decay. Since coatings can sometimes mask decay, one should also probe the wood with a knife or screwdriver to see if the wood can be penetrated easily. If so, fungal decay or even termites may be present. Once the wood is damaged by decay or termites, it is not salvageable and should be replaced as soon as possible to keep the rot or insects from spreading. Let's see what happens to a wooden structure during its service life with and without proper maintenance. Without any maintenance or replacement, the wood will deteriorate and reach not only the functionality, but also the safety limit much sooner. By fixing and replacing damaged elements that no longer serve their function, we can prolong the structure's service life. But with regular maintenance, we preserve the building's structural integrity and keep it looking good for most of the time, while also storing carbon in the wood material for longer periods of time. To sum up, just like any other building material, wood has its advantages and disadvantages. Knowing how it works, its possibilities and potential pitfalls, investors and professionals alike can plan and predict the performance of timber constructions and design them in a way to last and look beautiful for many years to come.
Okay, so that just gives you a flavor of some of the high-level content support that we have available, and as I say, a bonus outcome really from this this CLICKdesign project. We're going to switch back into Menti now, I think, if we can do that, because we're just going to engage with you once more, audience, and then we're going to move into a Q&A conversation. So if you have any thoughts and questions, certainly we would be interested to hear those and field those.
Yeah.
I think, are they doing it?
So this was, yeah, but I'm wondering if the browser is closed. Because I don't see Menti here.
Okay. Oh, something's happening. Okay, maybe while we're waiting to do that, perhaps if I could invite my colleagues up so we can progress into the Q&A session, because we were going to use this next engagement point. So Christian, Philip, Jonas, and also is Patrice here? Patrice Godno? Hello, hi Patrice from Swedish Wood, so he's going to join us as well. So perhaps while we're waiting for that, if we do, it's actually impossible for me to see the audience because the light's shining in my eyes. But if you do have any questions, raise your hand, or if there are any online as well, we can maybe use that to start the conversation.
There's still one mic missing.
Is there a microphone down here?
Eva.
No.
Yeah, thank you very much. So that was really impressive. So I'm wondering, after the lifetime of that project, how is the database and the tool being maintained?
Are we? Should we? Sorry, apologies. Can you hold that question? We seem to be back on Menti point.
Those of you connected to Menti, are you still connected?
So if you are still connected to Menti, alternatively, at the top there we've got the dial-in code again, if you need it. So what we're asking you to do now is just to rank the importance of factors. So you've got 4 factors, or you should have on screen: material durability, climate, product maintenance, and building design. Oh, it started, so it's working. We'll give it a minute to Jonas. I don't know if you want to. You going to sit with the rest of the group? Yeah.
Yeah.
Oh. 25 inputs, 29, 32. Interesting. Oh, material durability seems to be going up the ranking there. That. Can I perhaps ask, I don't know, have we got a roving microphone for you guys to use? Yeah. Yeah. Christian, I don't know what your thoughts are looking at screen there about the ranking that you're seeing from the audience.
Yeah, that's actually quite interesting. Also that it's changing a bit, the ranking here. I mean, we discussed this question quite a lot during the last 3 years, and yeah, actually we also have figures for that. So we could say, okay, the factor for different design details is between, I don't know, 1 and 3 or 1 and 5. And I can tell you that the factors for material durability are covering a much higher range. So it's between 1 and 17. So yeah, from a modeling or from a mathematical perspective, I do not fully agree with this ranking, but of course we have a couple of factors which are kind of KO factors. So if there is not enough moisture because you have a proper design with a lot of shelter for your cladding, for instance, then of course the dose and the risk for decay is 0. And with material durability, of course, you can reach quite a high resistance when you have using heavy-duty preservatives, for instance, but it will always stay biodegradable material. It will just take longer, but it's not a KO criterion. Mm-hmm. So that's maybe yeah, the important thing here.
Mm-hmm. Okay. So could I ask for that question to be repeated, and please speak as loudly as you can. It's very hard for me to hear down here. But
all right, so I take the mask down.
Excellent.
I actually was wondering, so after the lifetime of the project, how is all that material and the tool being maintained so that it's accessible later on?
So beyond the project lifetime. So, I mean, as Jonas said, everything you've seen is completely free and open access. We have developed the protocol. You saw a little glimpse at each stage into the science and the testing and the evidence to get to that protocol. So we're really encouraging people to engage with it, use it, critically assess it, and pick it up and develop it if they wish as well. And I know part of the project team as well, it's really heartening to see actually a continuation actually within the ForestValue program as well, working in the LCC Wood program as well. So some of this work will continue life in that form as well. But thank you for the question.
Can I add to the
yes, please do.
So I would say that at the end of the project, when we put an end to it all, then there will be some kind of version that is locked, fixed, that will not be changed. This will be the legacy of this project. But then development will continue. And as Ed said, everything is open source and open access. And we just encourage you to use this data. So this is, as you can see, the applications are very basic. And we just encourage companies with more muscles and more knowledge in web development and so on to use the data and just develop it further and make their own, integrate it with their own products. So this is also how it can live on.
Yep. Patrice, I wonder if I could ask you, what are your sort of thoughts around this challenge around, well, durability and performance? No.
Patrice Godonou. I am coming from Swedish Wood, which is part of the Swedish Forest Industry Federation. And our goal is, of course, to promote the use of wood-based material as building products. And as such, I don't totally agree either with the outcome of our survey here, but material durability will obviously be of great importance for us. And I think the speakers earlier today highlighted different aspects that are important for the public and end users. And it was interesting to see that the CLICKdesign project has addressed issues that are relevant for laymen, people developing their own small cottage or something like that. Also issues that are of importance for the handyman or contractors, and later for maybe structural engineers. And as we have seen earlier, there are no real standards today. I'm working with standardization, by the way. So there are no real standards really for durability per se. So this is something that we are missing. There are very good standards for the structural design, Euro codes. There are standards for the material, But what we miss would be something that I will say durability-driven structural design, a standard for that. And I think what you guys have been working on in this project is a way towards such a standard. Yeah.
Excellent. Thank you, Patrice. Interesting to hear that perspective. Any sort of thoughts or comments from the audience? Yep, Mika.
So I have the mic here, so could you put this on?
Yep, thank you. Yeah, thank you, Ed and team, for a very interesting presentation. My question is that have you been able to discuss and plan some dissemination activities after the project? So you said that it will stay open source tool for everyone, but how about the dissemination so that it would reach out the information you have created now to the larger audience?
Mm-hmm. Yep.
Oh, who wants to? I have two mics.
Yeah, there are several options. One is that Ed already mentioned. This will be another ForestValue project, Wood LCC, where we are continuing with the optimization of the models, but we will go one step further, and that is about life cycle costing, which is very closely, of course, connected to the question of service life planning. So that is one way, but we will also have the opportunity to present this approach on national level in the different countries that have been involved in this project. So fortunately, we could also have partners from outside the original ForestValue world. We have partners from Spain and from Canada. So also on international pan-European level, it was possible to spread this information. Mm. Yeah, and I think the rest will do this open access approach, web-based, and that is what we're working on. Mm.
Yeah, I mean, I can add a little bit from a sort of UK perspective as well. Certainly what has come out of this program has really changed direction in some of the technical committees in the UK. So we're very much continuing that pathway and utilising that well, it's a challenge we all face, really, isn't it? It's bridging that gap between practitioners and users, but also general public. So that whole kind of bottom up and top down approach. So we're certainly pushing it through those avenues as well.
And maybe I can add, because Patrice mentioned that it's very important to get into the standards, also in the European standards, and quite some of us in the project team are involved in TC38, that is the Wood Durability Technical Committee within CEN, and especially Ed, who's convener of a working party or working group that is responsible for performance classification of wood products, and that is covering the key standard EN 460. So what are the requirements for durability in different use conditions? And so during this project, we always had in mind that all this very complex and complicated modeling stuff should be able to break it down to a simple system that can be used and in harmonized standards. And I think it's that's a way forward as well within the different bodies within CEN on the European level.
Yeah, absolutely. And well, hot off the press in many senses. So the copy for final vote actually went out 13th of June. So it will be socialized as well very, very soon, which we're very excited about, which again is a major step forward in the world of standardization, which we all know, and Patrice and others directly involved. Very challenging, very technical, sometimes quite slow moving, but it's a true testament to how this project actually has supported that process, which has been very critical. Thank you. Are there some other comments or points? Yep.
Hello, my name is Thomas Alsmaker, Head of Innovation and Research at Swedish Wood. I would First of all, thank you very much for a very interesting presentation. Very important subject, and I hope there will be a life for this project after this. And I'm thinking about to what extent have you tested these tools in practice? I'm thinking about, for instance, architectural firms, engineering companies, contractors, and what was the response in that case?
That's an excellent question. Perhaps if I could start answer, and then perhaps you guys could pick up. So CLICKdesign had an industry group of 23 partners, which included indeed members from the engineering community, from the architectural communities, and they've been part of the processes of piloting the evolution of the modules that Jonas has shown us today. So they very much helped in that feedback process. There's always more to do. You know, we are continuing that process. We have to be completely honest that obviously coronavirus did impede us in part of our anticipated validation works, but we have conducted validation. Actually, Christian, or maybe your colleague did some.
Yeah, we did some validation. I guess we tested more than 100 wooden buildings, wooden components, and adapted the model here and there. So there are different screws that you can turn. Yeah, now we have the final version, which is quite well validated. But I think these are two things. What you mentioned is the applicability of the tool from industry side or from planning side, and the other is the validity of the tool itself.
Yeah.
Maybe I can add to that. Thomas is my colleague, but I've been involved in this project earlier than a bit like almost 2 years now. 1.5. And so I've been part of the so-called reference group from the industry that had to test this tool and assess its usability, so to say, or user-friendliness. And so I've been giving feedback to the group. And one application that we found is that we have interactive design tools on our website, Swedish Wood website. For those who speak Swedish, one of them is called byggbeskrivningar.se, and the other one is called tradradhuset.se. So on those sites, anybody, a layman or a handyman, can go and try to, for instance, to choose different type of facade materials for the walls or roof materials, and see how the aesthetic performance is. And one application, direct application that we saw for this output of Design Click is to couple your modules, your apps, into our apps, so that people in advance can make some sort of assessment of the service life of the component, wood-based component that they choose. And out of that, you could use the small shed design that you use coming from our tool. So we have already started integrating their apps to our online design tools.
Okay, thank you, Patrice.
Can I add one?
Very quick.
Comment?
Very quick.
So if you go back like 6 or 8 months, then the tool looked completely different. It was actually a MATLAB application. So one of the biggest and most impactful types of feedback we got from the workshops was actually the lack of feedback. Patrice was one of the few who actually managed to test the tool, because there was a lot of problems with installation. So one of the most the biggest types of criticism was the lack of availability. So that's why we changed everything and went for a web-based format instead.
Accessibility, absolutely.
Yeah.
Absolutely.
If no one can use it, then it's useless. Doesn't matter how good it is.
Right. Well, we need to draw to a close because we've run out of time. There's one sort of last bit of fun if you're still on Menti, just to do a bit of a word cloud. please type in any words that you feel appropriate in terms of durability. So as that word cloud shows behind us, I hope we've been able to demonstrate to you the significance and importance of durability and performance of wood in enabling wood in construction in all sorts of applications and uses. Really essential part of the future, whether a homeowner, whether a sort of wood purist in terms of the definition of delivering all wood buildings, or a wood pragmatist about utilizing materials where best and appropriate. Really fundamental to that. So it really just remains for me to do a few thanks. Obviously, I want to thank the ForestValue network and the sponsors particularly for what I personally believe is a really unique and visionary funding mechanism for research in Europe. We within the team have created the protocols, free to access, free to use, free to develop further and interact with, so please do that. Obviously, I'd like to thank all colleagues in CLICKdesign, those that are here and those that you've heard on screen who unfortunately couldn't be. An amazing achievement that's been completed in the last 3 years. And then just finally, thank you to our audience, online and in person, for your participation. Thank you very much.